Hi everyone, thanks you for being here today. My name is Taeyong Jun, and I would like to present my research project for my Master of Artificial Intelligence coursework program. The title of my research is Enhancing Vision-Based Analysis at MRT and LRT Fragate through Robust Unintended Object Detection, Crowd Evaluation Analysis, and the Small Object Recognition. This work is supervised by Dr. Irma from the Faculty of Computer Science and Information Technology. Let me start with the problem statement. We are trying to solve. CCTV cameras at MRT and LRT frigate already exist in almost every station, but they produce too many false alarms. Over time, operators stop trusting the system and real safety events get missed. We call this alert fatigue. When we look closer, we found that these false alarms are not at the same. There are actually three distinct types. First is a rule driven. For example, when a bag is left for a few seconds, the system fire an alert, even though the owner is just standing slightly outside the camera view. Second is screen control driven. For example, when a parent and a child walk through the gate together, the system thinks it is targeting. The last one is prescription driven, where the detector itself is wrong. For example, it sees an umbrella where there is no umbrella at all. The key insight is this: a single detector cannot fix all three types because each one needs a different solution. Based on this, I set three research objectives. The first objective is to design a three-layer cascade architecture where each layer is aligned with one of the three false positive types. The second objective is to evaluate a system through systematic experiment, testing every layer, then combining the best component together. The last objective is to validate the recommended system on new, unseen video footage. This objective lead to three research questions: how to design the cascade, which configuration works best, and whether the system can generalize to footage it has never seen before. This is the architecture I propose. The system has three layers working one after another. Layer 1, do basic detection. We use a YOLO VX detector combined with the tracker line like ByteTrack or BotSort plus single rules logic. Its job is just to flag candidate events like this bag have been here for a while and these two person cross the gate very close together. The layer 2 is use a vision language model, basically an AI that can look at an image and answer question about it. We test three models. The first one is Q1 2.5 VL, Q1 3 VL, and the last one is a Gamma 4. The model reads the candidate's events from layer 1, looks at the frame, and answers the structure question like, is the bag actually unintended? This filters out most of the easy false alarm. Layer 3 is at the extra truth, for example, zooming in the bounding box or showing the model multiple frames side by side. This is for the hardest case where the models need a closer look. The output goes one of two ways. If the cascade say true positive and an alert is sent to the operator. If it say false alarm, the event is slightly discarded. The important part is the layer 2. Handle the rule-driven and the screen context-driven false positive. Well, layer 3 handle the residual precision-driven ones. For the experiment, I used three public datasets. Aboda given us 11 videos with the real abandoned object events. These are our positive sample for subtask 1. Mod 20 gives us at crowd dense video. We use this as negative sample to test its test if the system fires false alarm. Rira got HD given us two higher definition video that we keep aside for final external tests to make sure the system can handle footage it have never seen. The three subtasks correspond directly to the three false positive type I mentioned earlier: unintended object tagging and a small object recognition. In total, the experiment has 178 cells, 78 cells for elation and 22 cells for cross combination across three random seeds, and 28 cells for external validation. We mentioned two positive keep red, false positive filter red, latency, and 95% of the confidence interval. Let us look at the layer 1 first. I test 5 configuration where varying the detector size, the tracker, the input resolution, and whether to use the tidy inference. Look at the result. The key finding is that no single configuration wins on all three subtasks. For the subtask 1, unintended object detection, the best is a C5 with the SAHI tally inference, which given recolor of the 0.727, that is 27 percentage points better than the baseline, but the cost is lower specificity. For the subtask 2, tackling all 5 configuration tail on specificity, but the C4 with high resolution has a low workload. For the subtask 3, small object recognition, C3 with a boson wins with specificity 0.947. Interestingly, the same C5 and C4 configuration that helps subtask 1 actually hurt subtask 3. So the conclusion is, carry the optimal layer 1 setting depends on the subtask. This confirms the value of designing the cascade around the false positive taxonomy. This slide is, in my opinion, the most interesting finding of the whole research. I test 3 visual language model: V1, Q1 VL at B, which is the news one released in 2025, V2, Q1 2.5 VL7B, which is the older and small model, and the last one is V3 Gamma 4 26B, which is the biggest model by parameter counts. The question is, which is the best for the recognizing intended objects? Look at the result. B1 failed completely. It get the true positive keep rate of 0.00 across all 5 prompts. V3 also failed completely, even though it is the largest. The only models that work is V2, which is the Q1 2.5 VL7Bs. The older and small one, it get the perfect true positive keep rate of 1.00, and it is also the faster and less than 3 seconds per event. This is a counterintuitive result. The common explanation is that nearest and largest models are always better. But for the surveillance trigger, this is not true. The benchmark numbers from the model release paper do not translate to surveillance performance. The takeaway is the model selection must be based on empirical testing, not the release date and the model size. For the layer 3, I test 6 different verification tools, from no tools baseline all the way to agentic function calling, where the model decides for itself whether to zoom in. The result here is what I call performance saturation. All 6 tools achieve perfect 2 positive keep rate and perfect 4 positive filter rate across all 3 subtasks. What this tells us is the cascade discriminative power is already concentrated at the layer 2 reasoning stage. The layer 3 tool does not change the classification outcome under in disruption conditions. Among the 6, I select T1, zoom in boundaries box as recommendation tools because it's given the lower latency across a subtask, and it produces a useful visualized effect that an operator can inspect. The architecture implication is in the development. Layer 3 can actually simplify to no tools without losing performance, but T1 is preferred when we want a visualized record for operator. In phase 2, I cross-combine the top 2 components from each layer. This given at stack per subtask, run across 3 random seeds for the 72 cells in total. For the subtask 2 and subtask 3, OS stack achieve perfect false positive, filter red at subsequent seconds latency. For the subtask 1, we see a precision recorder trade-off. The C5-based stack preserve all true positive but propagate some false alarm. The C1-based stack have no false alarm but on a smaller positive base. Based on this, I recommend 2 configuration. Configuration A, the balanced one. Use the C3 plus V2 with the ROPROM plus T1. It gives 0 false alarm across all 3 subtasks and sub 3 second latency. This is what I recommended for deployment. Configuration. The second one is a configuration B. The higher recall alternative. Use C5 plus V2 with ROPROM plus T1. It improved subtask 1 recall by 27 percentage points, by the cost of about 5 false alarm per cells. This is useful when missing a embedded object is more costly than a few false alarm. The choice between A and B depends on the operator priority. Now, this is the most important validation. I type configuration A, which was selected entirely based on the embedded and mod 20, and I apply it to 2 completely new HD video from the Brigade ground that the system haven't seen. The result is 20F out of 28 events correctly classified as false alarm. Zero false alert reaches the operator. The latency is around like 0.6 seconds per event, which is consistent with the in distribution phase 2 numbers. Let me go through one specific case. The umbrella case at the frame 6565. Shown on the right. Step 1. Layer 1 detect an umbrella and this bounding box with a high confidence. Step 2. Layer 3 crop the region and send the zoomer image to the vision language model. Step 3. Layer 2 use the V2 model with the raw prompts. Looks at the image and answer Q1 no, means this no umbrella is actually there. Step 4. The cascade predict is a false alarm in 0.6 seconds. This is directly instant level proof that cascade can correlate a confidence level 1 mistake on the footage it have never seen before. So it shows the system generalized beyond the dataset is what turns on. So, to summarize the contribution, for the academic community, this research contribute a new factorized that cross-combination methodology and events ground false positive taxonomy and a counterintuitive finding about the vision language model generated progression for the public transit operator. This deliver a deployable open big cascade with a null cloud dependency, 0 false alarm at sub 3 second latency, and a tunable high recall alternative. All components are permissively licensed, so this can deploy commercially. For the visual language model research community, this provides systematic empirical events on the three open bit visual language model under the structure zero-shot trigger, with 178 experimental cells and raw response preserved for the future secondary analysis. Overall, this work deliver what I believe is the first empirically optimal externally validated full open bit cascade for abandoned object detection in public transit environments. To conclude, my research established three principal findings. First, layer 1 configuration must be matched to the subtask. Second, the small and oldest Q1 2.5 VL model usually outperforms the new and largest alternative, a result that contradicts the commons hierarchy. Third, layer 3 verification reaches a rich saturation, means the cascade discriminative power lies at the layer 2. The external validation confirms that the cascade correctly suppresses 28 out of 28 false alarms on unseen footage, including the umbrella case. The recommended configuration for the deployment is C2 plus V2 with a row prompt plus T1 zoom-in box, delivering zero operator phasing, false alarm across all three subtasks at sub 3 second latency. So, thank you for your attendance.